There are some that you'll be graphing, and we'll be graphing some today, so you can see how to do that. But the first 3 through 8, and then 28 and 29 are all graphing. So please make sure that you do graph those problems. The other ones, you'll be kind of writing an equation, or we call it a formula when we're talking about a sequence. And then the cumulative review that was assigned yesterday after the test, that is due on Friday. And your tests have been graded, posted to Google Classroom. I still have 2 students that need to complete the test. And once they get them completed, I will give those tests back to you in class. So if you want to go to Google Classroom, if you haven't done so already, and please upload and send the Chapter 12 notes packet to your Notability. If you've already done that, thank you, appreciate it. So we're looking at Chapter 12, and if you haven't, at this point in the year, I really hope that you have your Notability organized, but I would strongly suggest that you start to at least pull your math stuff together, your English stuff together. You're going to be using Notability definitely for the rest of your high school career, if not beyond that. So make sure you start keeping it organized. So, cute little comic that I have here talking about a specific sequence and series that we're going to actually talk about today. And we'll see what kind of pattern that makes in a little bit. But we are going to start with this little square, colored square with green and white. And actually, I guess it's white and black stones, but mine came up green. So for some reason, the diagram was green. A large plaza will be covered with the same size white, and I'm going to say green stones, since it's green on our screen, to make a pattern. So we have a plaza, and they're covered in these stones to make the pattern that's shown. It says the pattern starts in the lower left corner and expands. Find the number of white stone squares in the 8th band of white squares. And then it says to justify your answer. So if you look at the white squares, our goal is to figure out the number of white squares that would be in the 8th band of white squares. So see if you can think of a way to determine how many white squares would be in the 8th band of white squares. So Valerio, how many stone squares are in the 2nd band of white stone squares?
5.
And then how about in the 3rd band?
9.
So the 4th band would be?
13.
All right. So what do you notice about those numbers, Valerio?
They're all odd.
They're all odd. So we have all odd numbers, and that's because of that little corner box. So you have an even vertical and horizontal, but where they meet, that makes it the odd number. Well, how else could what else could we look at looking at these numbers? What else do you notice? Anybody else notice something different about the numbers? Malachi, what do you notice?
They're all increasing by 4.
Yeah, so if we continue that pattern, Malachi, what would the next group be?
17.
And then
21.
keep going.
25.
And finally?
29.
So how many squares are in the 8th band?
29.
Yeah, 29. So you see that this pattern, nice job, Malachi. We have a pattern here of numbers increasing by 4. And the question said, find the number of white stone squares in the 8th band of white squares. So there would be 29 white squares. And you can find that just by noticing the pattern and continuing that pattern on until you get to that 8th band of white squares. So that kind of takes us into what we're talking about today and what we will be focusing on for the next week and a half or so till we switch to the series instead of the sequences. But a sequence is a list of numbers like I have above. But that list of numbers contains a pattern. And the sequence or this list of numbers above is called a sequence, and there's a pattern. So it is a sequence, it contains a pattern. So the second word we have here is the terms of the sequence. The terms of the sequence would be each value of the sequence. And there's two things that we are going to look at. Each term of the sequence has a specific position correlating with the actual term that we're finding. So the position would be like first position, second position, third position, fourth position, fifth position, and that could go all the way on to the last position, which I'm going to call an N. So think if you're in the orchestra, you're in the first chair, the second chair, the third chair. So there's a position that you're sitting in the orchestra. So our terms of the sequence have a position as well. And then using the numbers from above, we had a 1, and then a 5, and then a 9. And then that would go on and on and on to my last position. But the first term would be 1. The third term or position is 9. The fifth term is 17. So if I said find the fifth term, find the 8th term, you would know that you have to find the 8th number in the sequence. Sequences are notated a little differently, and a sequence uses the notation A and then sub N. Sequences use subscripts. So a sequence still uses a variable, but it no longer uses the variable X. So the notation A sub N is the notation that you will see to represent a sequence. And the N is going to be the position that you find. The next two vocab words we have are finite versus infinite. So if something is finite, Eva M., what does it mean if something is finite?
I'm not sure.
Do you know what infinite means? The other one?
It goes on forever.
Yeah, so an infinite sequence is a sequence that continues without stopping, that goes on forever. So an infinite sequence goes on forever. So maybe I had 2, 4, 6, 8, 10, 12. And then an infinite sequence is going to have those 3 little dots that show that it continues on. I think those dots are called ellipses. I could ask Mr. Kane. An infinite sequence goes on forever. It doesn't have a stopping point. So then a finite sequence, we say, has a last term. or you could say it ends. So maybe my sequence was just 2, 4, 6, 8, and 10. Notice the sequence is usually listed with commas in between the numbers. So it has a last term, it stops. An infinite sequence is going to go on forever. So we're going to see if we can look at a couple of examples of sequences to try and see the pattern in the sequence. And then we're also going to try and write an equation or a formula to represent the pattern in the sequence. So the first equation here is actually a very famous sequence. So we have the numbers 1, 2, 3, 5, 8, and 13. And then it continues on. It goes beyond 13. So any sequence that continues on, you'll see those little 3 dots. It says it's a naturally occurring sequence, and it's called the Fibonacci sequence. So Fibonacci was a mathematician, and he kind of created this list or noticed this list of patterns, this list of numbers happening with a specific pattern. If you have watched or have read the Da Vinci Code, so my daughter is currently reading the Da Vinci Code. Has anybody read the Da Vinci Code or watched the Da Vinci Code? No? Good book. Very historical. But this pattern occurs in the Da Vinci Code as to one of the things that they have to try and find or solve in order to find the next part in the show or in the movie or in the book, whichever you prefer to look at. So there is a pattern in this list of numbers, and the pattern's a little hard to kind of distinguish. And that's going to be one of your goals tonight. Can you distinguish the pattern in the list of numbers? So look at this list of numbers. Try and think, what could you do with these numbers? How is the next one created? So how could I go beyond 13? What's happening with these numbers to find the next value in the sequence? And that's the goal. So what do you do with the number that you have to find the next number? Or how do the terms find the next number? Anybody have an idea? You're really going to have to think outside of the box for some of these. Ella, what do you see?
I'm just going to use the 3 as an example. You add the 2 numbers before it to make 3.
Yeah, so you're saying these 2 add together to give you 3. So then what else, how else would that continue to work then, Ella?
2 and 3 makes 5. 3 and 5 makes 8.
Yeah.
And 8 is 13.
Nice. And then my next number would be
21.
Yeah, 21. So you're adding the 2 terms to get the next number. Nice job. Riley, did you notice that as well?
Yeah.
Nice job. Good. This one's tricky. So it is called the Fibonacci sequence, and the pattern would be, we could say, add the 2 previous, we'll use that word, terms. And remember, that word terms refers to the numbers in the sequence, but you're adding the 2 previous terms to find the next term. So it wants us to find the 8th term of the sequence. And right now they give us 6, and Ella said that the next one would be 21. So that would be the 7th term. So Riley, what would the 8th term be?
It would be 34.
Yeah, it would be 34. So you're pairing the 2 numbers together to find the next term in the sequence, and that 8th term would be 34. So again, the term that you're asked to find would be the fact that you're finding the 8th number in the sequence. The 8th term is 34. The way we would write that, we would say A with the little subscript of 8. So the A represents a sequence. Instead of using a Y, or an f of x, we use an a to represent a sequence. And then the 8 says we're finding the 8th term, and that's equal to 34. So that's the notation that you're going to be using for sequences. So a sub 8, it's a subscript, so we say sub, a sub 8 equals 34. All right, let's check out the next one. So we have 2, 5, 8, and 11. Describe the pattern of the sequence. Anybody describe the pattern here? Jaden, what do you think?
Would it just be counting by threes?
Yeah, counting by threes, you could say adding 3. So you're adding 3 each time. The next thing that I want us to do that it doesn't ask us to do right here, I want us to see if we can write a formula, which is kind of like an equation. So when we write a formula, I want to write an equation that I could use to find the next term. And I'm going to write over here equation. A formula has to have a variable in it. So Jaden said you're adding 3 each time. So if I thought by adding 3 each time, or you're counting by threes, I think that's what she said. She said counting by threes. So I would continue to count by threes, starting with the number 2. I can write an equation for that by saying if I take 3 times n, which n is the position of the sequence, and then subtract 1. I then have a pattern to represent the numbers of my sequence. So let's look at this. If I plug in a 2, if I want to find the second term, so here's my first term, second term, third term, fourth term. So if I plug a 2 in for n, I would have 3 times 2 minus 1. Well, that gives me 5, which is the second term. So the number you plug in for n represents the term in your sequence, and it should match up. So 3 times n, Jaden said you're counting by threes. So that's how I would write that, 3 times n, counting by threes. But you have to subtract 1 because you're starting with the number 2. So that's why I'd have to subtract 1 there to get that starting point. All right, let's look at part B. Graph the sequence by plotting 6 ordered pairs. The ordered pairs should be the position, comma, the term. So the first position has the number 2 in the sequence. We're going to make that an ordered pair. The second position has the number 5. The third position is 8. The fourth position is 11. Jaden, we're asked to find 6. So what would be the 5th term of the sequence?
14,
And then the 6th term is
17.
17. Nice. So we're going to plot these as points. Notice that the graph is counting by 2s. See if you can plot those points. The y values are counting by 2s. So the x's are just counting by 1s. And notice that it is labeled as a sequence. So a sub n is the number in the sequence. The n would be your position. So n is the position. And then a sub n represents the term. So the axis is labeled to graph a sequence. So up to 2, and then 5, and so on. So then the next question, after you have a graph, it says, does the sequence appear to have a limit? This word limit, you will be seeing that word, that term throughout mathematics. And a limit means, is it approaching a number? So does the sequence approach a number? Does it have a limit? If it approaches a number, it should get really, really close to that number. So think about the asymptotes that we graphed in chapter 8. The graph approached the asymptote. It got really, really, really close to it. Almost that it kind of became horizontal if it was approaching the horizontal asymptote. The graph kind of went horizontally along that asymptote. If you look at our graph, it looks like it's just continuing to go up further and further and further and further. And it's never going to approach or get close to a number besides the number infinity. So we would say this graph does not have a limit because the graph continues to increase. Because it's going up by 3 each time, and it's just going to continue to go up and up and up and up. So look at the graph and you can see that it's just going vertical. It almost looks like a line. Notice I didn't connect these points. I didn't connect them to make a line because it's not a line. We're not graphing y equals mx plus b. We're not graphing a function. This is just a sequence. And the only numbers that exist are the numbers in the sequence, not the numbers in between. So I don't have a 1.5 as a position or 2.5 as a position. It's just the whole numbers as the position. So let's look at number 2. Part A, extra example 2A. This one says describe the pattern. Can anybody describe the pattern? -2, -4, -6, -8? How could you describe that pattern? Brooke, what do you think? What could you say for that pattern?
You subtract 2.
Yeah. So you're subtracting 2. All right, the second part, it says write a rule for the nth term. That's the same thing as saying write an equation or write a formula. So we want to be able to come up with an equation or a formula to represent this sequence. So we're going to say a sub n instead of y equals. Brooke said you're subtracting 2 each time. And because you're doing that every single time, it's going down by 2. My formula would be -2 times n. Each term, I'm subtracting 2. So this works very similar to y equals mx plus b. My slope, if I had a slope, my line would be going down 2 each time, or my line would be going up 3 each time. So it's very similar to that. We're going down 2 every time, which means I have to take -2 times n, the position of my sequence. Because this first number in the sequence starts with -2, if you plug in a 1 for n, that makes the first number of the sequence. It is -2. So we don't have to subtract anything from this -2n, because once you plug in a 1, you get to that first value in the sequence. So our rule or our formula would just be -2 times n. Whereas the previous one, we took 3 times n because you were adding, 3 each time, but the first number started with a 2. So we had to subtract 1 to get it to start at the number 2 instead of starting at the number 3. If I didn't have that subtracting 1 there, then my first term would start at 3. And it doesn't start at 3, it starts at the number 2. Questions on that? So when you're trying to write a pattern, think about what are you doing each time? So I'm adding 3 each time, or we're subtracting 2 each time. That actually becomes multiplication when you're writing the equation. And then do you need to add or subtract anything from that in order to get to the first number? Ava.
On the previous one yeah. Why? So if you had to start with 3, why were we subtracting 1?
Okay, so if I plug in a 1 to find the first term, 3 times 1 makes what?
3.
That 3 needs to match with the first number in the sequence.
Oh, okay.
It doesn't, but if you subtract 1 from it, then you get 2, which is why I
Okay.
had to subtract 1. The second one we did, when I plug in a 1, I get a -2, and my sequence starts with -2. But if that
Okay.
sequence started with a different number, then I might have to subtract something. Does that make
Okay.
sense?
Yeah, that makes more sense. Thank
Good.
you.
Yep, I'm glad you asked. Good. All right, so let's graph this. The second part here, graph this, or the third part, graph the sequence by plotting 6 ordered pairs. So again, position, term, position, term. And you're given 4 numbers in the sequence. We want to graph 6. And this is what part of your homework is going to be doing. Part of the homework will be just plotting points and graphing the sequence. So my 5th position would be a -10 if I continue the sequence. The 6th position is -12. So a good bit of your homework is graphing sequences. And then you're going to plot those points. Your graph paper that's provided for you today is sequence graph paper. And you'll just have to make sure that if it's a negative sequence with negative values, make sure you choose the negative one from the graph paper. I have both on there for you. So this is going down 2 each time. Again, you don't connect the points. It doesn't make a line. Yes, it appears to have a pattern because it does have a pattern, but we do not connect them and make a line. This is not a y = mx + b. It's not a linear function. It's a sequence. And then finally, does this sequence appear to have a limit? So Ava R., I'm going to come back to you. Does it look like the graph is approaching or getting really close to a number, or is it going to just continue to go down?
I think it's going to continue to go down.
Yeah, so then we would say it does not have a limit. All right, so we're going to look at one more. See if you can describe the pattern. So 9, 3, 1, 1/3, 1/9. Madison, what do you think the pattern is here? How would I get from 9 to 3? Ella, how do you think we'd go from 9 to 3?
Divide by 3.
Yeah. So you're dividing by 3. So then it says, write a rule for the nth term of the sequence. How could I write a rule for the nth term of the sequence? Jaden, what do you think?
So I know it would be like a sub n and then like equals n divided by 3. But then I don't know what you would need to do to get to that 9 to start with it. That's what I'm confused about.
Yeah. So you're right. We need to be able to get to that 9 by plugging in a 1. So what could you do with that n?
So would I make that trying to think, would it be 27? That might sound crazy, but because it would be like 27 divided by 3.
Right. So you
Something like-
took, yes, and I understand. Yeah, because you would do 27 divided by 3. And then
Or
you
would it be 9? Just itself. I'm sorry, I don't know.
yeah, this one's a little tricky. And for I think we'll talk about more of this one tomorrow for the looking at the time. I want to be able to graph it. So let's leave this for tomorrow. Put a little star next to it. And we'll talk about how to try and get this rule tomorrow. But I want to be able to graph it because I want you to see what this is looking like. And Jaden, I don't mean to cut you off because you are on the right track, but I just want to make sure we can graph this so that we can kind of see what this looks like. And then there's one other question that I want to make sure that we get to. So let's see if we can graph this. So first term is 9, second term is 3, third term is 1, fourth term is a third, fifth term is a ninth, and it says plot 6, so you've got to get one more, and that would be 1/27. So you're dividing those by 3, or you could say multiplying by a third. That would be another way to think of it. So when you go to graph these, notice how that graph starts to curve. And the last 3 numbers are really close to each other. So this graph does have a limit. And you could say the graph curves, or the sequence curves. What number does it look like they're getting really close to?
Zero.
Yeah. So we'll say there is a limit because the graph is curving and it's approaching 0. So that's going to be the difference if a graph has a limit or a sequence has a limit or if it doesn't. So is the graph curving towards a number as if there were an asymptote there? So think from the last chapter that we just did. If it gets really close to a number, then it has a limit. So this is approaching 0. All right, so there's one other problem that I want us to look at, and that would be finding the terms of a sequence. And I said that there's definitely algebra involved in this, which is why Mrs. Lucas and I were talking and we decided to skip probability and statistics and continue just going on with the algebra. And we'll go back to probability and statistics the last 3 weeks of the year. But this one, it gives us the formula. So notice here, that's the rule or the formula for the sequence. And over here is B. We want to find the first 3 terms and the 10th term. And this is actually probably the easiest thing we can do. To find the first term, you plug in a 1 for n. And notice I'm using that little a sub 1. So to find my first term, I plug in a 1 in the equation or in the formula. And it does look like y equals mx plus b, but it's using an n to represent a sequence. So Gabby Soul, if you plug in a 1, the first number of your sequence is
3,
and then if we plug in a 2, Gabby, you get,
5,
and the plug in a 3, you get,
7,
oops, that's a 2. So how do you think you'd find the 10th term, Gabby?
you would plug in a 10,
You'd plug in a 10. And when you plug in a 10, you get,
21,
yeah. So that's pretty straightforward. Let's look at letter B. So letter B has B sub n equals 2 to the 1 minus n. Well, this is just like saying f of x versus h of x versus g of x. Let me write these numbers up here. So for part B, you're going to do exactly the same thing. We just used a different letter to represent a different sequence. So Jordan, we plug in a 1 to find the first term. And then we get 2 to the 1 minus 1. What would that really be, Jordan?
2 to the 0,
Which is
1.
1. All right. If you plug in a 2, you get 2 to the negative 1. What happens when you have a negative exponent to a number, Jordan? Do you remember?
It turns into a fraction.
Yeah, nice. Turns into a fraction. So let's try 3. 1 minus 3 would be 2 to the negative 2. So that makes,
1/4.
nice job. And then we're asked to plug in a 10, which is 2 to the negative 9. You know what 2 to the 9 is?
No, I don't.
Do you have a calculator on you?
I don't. I'm sorry.
That's okay, you're fine. Somebody have a calculator? 2 to the 9th?
$512.
Thank you, 512. So you can see that this pattern, and then we go to 512. This one kind of looks similar to the one that I told you to circle, and we'll come back to tomorrow. So when there's an exponent, it kind of looks like you're dividing by 2, even though it's written in that exponent form. So we will talk about that one tomorrow. Again, you have some homework. It's going to predominantly be graphing and finding terms in the sequence. We will continue with this section tomorrow. Have a fantastic Wednesday. Stay warm.
Thank you. Have a great day.
Have a good day.